Hello, Physics 2. Welcome back to part 2 of Thursday's lecture. So last time I just wanted to recap real quick. We left off on Maxwell's equations. Let me go ahead and zoom out here so you can just see them all in all of their glory. So ever since chapter 21, we have been working towards these derivations, although you'll see that we actually started to lay the groundwork to go after Maxwell's equations starting back in chapter 13. So these describe fields in space. I once had somebody that talked about, not a student of mine, a colleague of mine, who talked about the experience of taking Physics 2, and they said to me, you know, we did all this stuff, and then all of a sudden we get to these equations, and it just all made sense. Why didn't we just do them from the very beginning? And the reason for that, if you're wondering that yourself, is that I have consistently found that by building slowly towards this, into this glorious crescendo, is that you can really appreciate what these equations mean, what they can do, and how powerful they are. Also, we get to do this in an order that is consistent with the order of which these discoveries were made, which is often not the case in a lot of topics that we cover within science classes, as we do it in just in a more natural order. But there's something about this that even though this is very highly empirical, highly technical, that almost seems mystical and guided. That we would get to these conclusions after really a century of work. So that's the reason I get so excited about them, is that they're really just stunning in what they do. And we wouldn't have modern physics theory if it wasn't for all of the equations that we learned in Maxwell's and everything this did for our understanding of electromagnetism and fields. In fact, there was a recent publication that just came out on the T2K neutrino experiment that shed more light on neutrino theory, which has implications, and you could stem this all the way back to the foundations that these equations laid. So that's why I take the time to really build them, is because I hope that by the time we get to this point of the semester, you can just appreciate what they are and what they mean. And of course, along with that, we also talked about the net electric and magnetic force as one complete equation. So we can see we've got QE here, QV cross B, which goes along with Maxwell's equations. So of course, to study, these can be studied in more detail in a standard electromagnetism class. You will see them again, though not in such rigor. If you take an optics course, well, an undergraduate optics course, you'd see them very rigorously in a graduate level optics course. But these, these are it. This is the theory of light, which is what we're going to start building into next. Okay, so recap over. And let's start going into the next section of chapter 23. Fields traveling through space. So, we know that if you have a non-zero change in magnetic field with respect to time, then you have an associated E non-Coulomb. And we also know that if you have a time-varying electric field, then you have an associated B field that goes along with that. And this, by the way, I'm just going to say this now, you are looking at the premise for what a photon actually is. It's building towards this. It's a mathematical concept that exists in physical reality. All right, so to build towards that, we might ask, can a time-varying field exist in empty space? Without charges or currents? So far, we have talked about fields associated with electrical currents. We have talked about fields associated with magnetic dipoles. We have talked about fields associated with charges. Now we're going to progress towards the pure electric and magnetic field and whether or not those can exist on their own, which involves a little shift in how we think about these fields. So here is the guide for how we will think through this. And we're going to do this because this works for any problem as a reasoning guide. And this is also sort of the beginner level of the type of reasoning you do in subsequent more advanced classes. So if any of you will be here next year and are interested in taking modern physics, you'll see more of this style of reasoning in terms of how do you perceive the unseen. And by that I mean what we as humans are not capable of perceiving in a physical way in our imaginations within our brain. So these are physical things that exist, but we have to model them, we have to measure them, we have to trust our instruments and trust our mathematical computational models along with those instrumental measurements. So it's not that they're unseen, it's just that we don't really have a context for envisioning them. It's like trying to, we know about infinity, but can you envision infinity? No. And anyone who tells you otherwise has gone insane from studying infinity. I kid, but I don't. Okay, so here's what you do. First, you need to suggest an idea for an arrangement of electric and magnetic fields in space and time. So the first time you get to really play with space-time, we'll do it on a barely in this class, but it would be in an electromagnetism class. You do get to play with space-time in a modern physics class. You normally get to meet the Lorentz boost in that class, which you work in four vector space, which is time and space. It's way cool. It's one of those moments where it's like, oh, this is why I study physics, because this is really cool. All right, so we want to check it with Maxwell's equations. And we're only going to be using the integral version. And remember, for those of you who are in the algebra-based class, you'll never actually take an integral. It's going to be a path where you can easily calculate the perimeter or the surface area where you can easily calculate what that is. And you might, if you're in the classical class, I make no promises as to whether or not you'll have to calculate an integral, different expectations. But what I really appreciate about Maxwell's equations is even though they are calculus-based equations, we can understand them conceptually even without a study of calculus. So check it with Maxwell's equations. If it works, it's possible. If it doesn't work, it's not That was a nice theory. Maybe you can make a pretty little mathematical model with it, but it doesn't describe physical reality. It doesn't describe this universe if you want to go into multiverse theory. So think about what these fields would do to matter. And then think about the phenomenon associated with these fields. So, and here's where I'm going to differentiate between an experimentalist and a theorist. An experimentalist is going to think, what can I measure in terms of the phenomenon? And a theorist is going to think about, what can I derive, calculate, or model as a result of this phenomenon. Okay, so we've gone through those criteria. Now let's start setting up the thought model. So, remember how I said light is electromagnetic radiation. We first introduced this in Chapter 8 in Physics 1. And as I just hinted like 3 minutes ago, we're going to understand it more deeply and more intimately in this chapter than, unless you've studied this before, than you have previously. So, could you imagine light moving through, could you imagine? It just reminds me of that I Could Only Imagine song. I was on a worship team for a while. I sang that far too many times. Could you imagine light moving through a space free of charge? I mean, sure, we see starlight. Space is an empty vacuum. So, yeah. So, but it's moving. Thus, speed is non-zero. Obvious, but this is important. Okay, so let's analyze a single moving pulse. So photons, those beautiful wave-like particle objects, are just like little energy packets. They're way cool. So, something to know, electric fields are perpendicular to magnetic fields. So, if we look at the propagation of our pulse, it could look something like this. So let's see, I want to use really different, let's say these are the E fields. And do E in orange. I almost asked you what color you'd like me to do for the fields and realized that you cannot answer me. And we'll do our B fields in blue. So they're perpendicular to each other in 3 dimensions. So perpendicular and in 3D. So really we've got B in this case is coming out of the board. So this would be our B, because it's not, 3D is hard to draw in general, and it's really not my strong suit. Okay, so we can enclose this, our pulse, in a slab that moves with it. So let's see, I'll just redraw. And then eventually I'm going to stop labeling. So kind of so we've got our slab. It's moving with V. Okay. And so this is all moving together. And so now remember, electromagnetism and electromagnetic radiation depends on the perspective of the observer. So we need to actually make a decision about how we're going to observe this pulse. So let's say you're right here, and it's going to come towards you. So the pulse is coming towards you. Remember that picture. So coming towards you. So you will observe that both the change in electric field and the change in magnetic field are non-zero. So we've got some flux going on. And so the electromagnetic field in that drawing is propagating to the right. And when we use propagating in this context, propagating means to spread into a new region. Okay, so this is our setup. Now we're going to check it with Maxwell. So it's coming towards you. You are observing a changing electric field and a changing magnetic field relating to this electromagnetic little pulse. So Gauss's law. E dot n hat dA is equal to 1 over epsilon naught. Sum of the charge. Ooh, that's a really funky epsilon naught. Okay, we're going to isolate E and enclose in a Gaussian surface. So we've got E is orange. That's a box. It's not a pretty box, but it is a box. And let's give it some, we'll just use green. Some normal vectors. Okay, so a couple observations. Top and bottom cancel out. And sides are 0 because the electric field is parallel to the normal vector. Okay, so basically there's no charge inside. This makes sense. I'll write that out again. No charge inside. But I didn't say there was a charge inside. We just have a little pulse, just a field, no charge. Okay, makes sense. So far, so good. 3 more checks. Gauss's law for magnetism. All right, we're going to look at our magnetic field. Once again, we'll put it in a box. So let's see our magnetic field. There's our magnetic field. You can find better pictures in your book and online. All right, so the magnetic flux on one side cancels the other. And for everything else, B is perpendicular to n hat. So no magnetic monopoles. And this works. You get the desired result, which is a big fat 0. Okay, moving right along to Faraday's law. So it's passed 2 out of 4 checks. By the way, notice we've not done a single calculation. This is all conceptual. Now, you can do these calculations. I have done them many times. They're kind of fun to do, actually. I mean, I remember enjoying them. I haven't done them in a while. So, E dot dl is equal to minus d dt, B dot n hat dA. So, E and B are moving. So dB dt is non-zero, which implies a non-zero curly electric field. So essentially what we've got and we've got our electric field, our magnetic field, and then it's moving, so some h, it'll go some distance v delta t. I've got our v here. So that's what we're looking at in all of my artistic glory. All right, so in delta t, V increases by V delta t. So we get the change of magnetic flux with respect to time is equal to BVH. Oh my goodness, we've seen this before, which is equal to EMF. We then relate this to the electric field. EMF is equal to E dot dl is equal to, so this is equal to H, so therefore this is EH. Cosine of 0 is equal to EH, which implies EH is equal to BVH. Cancel, cancel. E is equal to VB. All right, so checks out. We've seen this before. Fantastic. Ampere-Maxwell is up next. So we have B dot dl, is equal to mu naught I enclosed plus epsilon naught times the change of electric flux. And so we're going to break down our pulse. So there are no currents. It's in space. What would be making a current? So I enclosed is 0. However, the slab is moving. Therefore, the change of electric field with respect to time is non-zero. So we've got looking at the other side, now the electric field is coming out. All right, so in time delta t, the electric field increases v delta t times h. And electric flux increases by EVH delta T. This leads to the change of electric flux being equal to EVH. And now we need to deal with the B side of the equation. It's like the B side of the record. So B dot dl is equal to BH cosine of 0 is equal to BH. This is because dl is just h. It does not look like an h, now it does. So if we put it all together, so B dot dl is equal to mu naught, sum of the currents enclosed plus epsilon naught times change in electric flux. So this is equal to BH, this is equal to 0, this is equal to EVH. So we have BH is equal to mu naught epsilon naught EV H. H is on both sides. And we get B is equal to mu naught epsilon naught E. All right, so we've got an interesting relationship to set up, and I'm actually going to leave you on a cliffhanger. And we're going to go through the implications of this on Monday's lecture. So I will see you then. Have a good weekend.